Today we're going to learn about fatigue stress concentrations. Now, before we get to the effect of fatigue, let's remember the effect of stress concentrations under static conditions. So that is, for example, we have a plate of an infinite width and length, and that plate has a circular hole in the center of it. Stress in this plate is usually calculated in the net area in the vicinity of that circular hole. And due to the presence of that hole, the force lines that flow through the plate concentrate at the edge of the circle, and the maximum stress that we see near the hole, at the edge of that hole, is much higher than the net stress that's applied in the vicinity of the hole. So this net increase in stress is what we call a stress concentration. The nominal stress is simply calculated as the force applied over the net area. We're under a static loading condition, and the maximum stress at the hole is equal to kT times sigma naught, where kT is the static stress concentration factor. This kT value comes from the geometry and the loading conditions of a particular body. So if we had a different type of geometry, we'd have a different kT factor, right? In our textbook, in the appendix, for many different geometry and loading conditions, we have stress concentration factor charts, which can help us to figure out what the kT is for a particular geometry. Now, an important thing to note for static stress concentration factors is that when we have a ductile material, that means a material that has a ductility greater than 5%, we set the kT value equal to 1. Instead of using the design charts, we assume, since it's ductile and there's a good amount of plastic deformation, that the maximum stress that we would see under brittle conditions isn't actually reached. Instead of stress rising, we plastically deform. And it's more appropriate, rather than using kT factors, to use something like finite element analysis to figure out the actual state of stress. But for brittle materials, where ductility is less than 5%, and for static conditions specifically, we do use that kT factor. We go to our appendix, we find the appropriate chart for our specific geometry and loading conditions, find the kT value, and then we plug it in to find sigma max. So now, let's consider fatigue loading conditions. Now, in fatigue loading conditions, rather than loads being static, instead our loads are cycling. They're going up and down. It could be pulsating tension, it could be fully reversed, it could be pulsating compression. It is loads that are changing periodically over time in a structure. Now, similar to the static condition, under fatigue conditions, there exists a maximum stress, where the max stress is equal to a Kf factor times the nominal stress, where Kf is our fatigue stress concentration factor, right? So a factor related to fatigue. Now, Kf applies to all fatigue stresses that are related to 0. So specifically, Kf applies to sigma max during fatigue, sigma min during fatigue, the stress amplitude, as well as the mean stress during fatigue. Kf is applied to all of those, right? Now, there is also a difference in the way that we treat stress concentration factors between static and fatigue conditions. Something to note is that some materials are not fully sensitive to stress concentrations during fatigue. The materials that would be sensitive under static conditions are not fully sensitive under fatigue due to differences in localized plastic deformation. And so the fatigue stress concentration factors, whether it's the axial ones or the shear values of the factors, are always less than or equal to the static values, meaning they're not fully sensitive to the concentration. The relationship between the fatigue and static factors can be rewritten as a notch sensitivity factor Q, where Q is equal to Kf minus 1 divided by Kt minus 1, where Q is between 0 to 1, which relates to not sensitive or fully sensitive. Now, that not sensitivity factor Q accounts for that plastic deformation that occurs at the notch during fatigue, which acts to lower the stress concentration. So rather than applying just the Kt equal to 1 during fatigue, instead we'll input the value from the Kt chart and then calculate Kf using the Q equation. Now, a very important thing to note during fatigue, is that for fatigue, both ductile and brittle materials are going to be evaluated with a Kt parameter. With static conditions, if we have a ductile material, we set Kt equal to 1. But for fatigue conditions, because we have that notch sensitivity parameter, we are going to find the Kt for the material, no matter if it's ductile or brittle, we'll find the Kt value. We'll, if given the Q, the notch sensitivity value, we'll use that, and we'll find the resulting Kf for our problem, right? Now, solving for Kf and Kfs, which is the shear version, simply as rearranging that Q equation, where Kf is equal to 1 plus Q in brackets Kt minus 1, right? Now, where do we get the notch sensitivity factors? The notch sensitivity factor Q can be obtained from charts. An example of one of the charts we have is figure 626 from our textbook. There's a couple of other charts. These are basic charts for steels and aluminums. In this first chart, we can see a couple of things. We can see notch sensitivity on our y-axis going from 0 to 1. And then we can see notch radius in inches at the bottom and millimeters at the top, going from 0 to some larger value. How do we read these charts? Well, say we're given a material and we know its tensile strength, we know its radius as well, the radius of the feature of the stress concentrator. Well, we can put that radius, the notch radius, into this chart. We can plot down to the tensile strength of our material, and then we can plot over to find the notch sensitivity factor for our material and the specific geometry that we have, right? Using this Q, we can then calculate the, we then will need to get the Kt parameter, and then we can calculate Kf, right? Let's also note that for this particular chart, this chart is for reversed bending or for reversed axial loads. We also have a figure 627 for reversed torsion. So this factor also depends on the loading condition, the loading type. So we'll need to be careful in selecting which of these charts to use. Now, these charts are all fine and dandy, but charts are a little bit hard to read, right? They can be subjective on, what is the exact value of the Q parameter that we're going to use. An alternate form exists that can help us to be a little bit more accurate in our calculation of notch sensitivity. Neuber and Kuhn described notch sensitivity as a function of the notch radius and a material's characteristic length dimension, the square root of A, where Q, notch sensitivity, is equal to 1 divided by 1 plus the square root of A divided by the square root of R. There is also a relationship for Kf, which is a function of that characteristic length. The Kt parameters, of course, we can pull from the appendix. The R is the notch radius, and then the Neuber constants is something that is experimentally determined for each material. Now, the advantage of this Neuber constant is that rather than having charts for finding this constant, instead we have polynomial functions, where the Neuber constant for steels under bending or axial loads is one of these two polynomials, depending on if we are in KSI or megapascal. And then for torsion, it's one of these two polynomials, again, if we are in KSI or megapascal. With these polynomials, we can directly put in the tensile strength of our material and get a specific value for this characteristic length, use that value in our radius to get an exact value for Q, and then solve our problem a little bit more consistently. So if ever we need a more exact or repeatable solution, as long as we know the tensile strength of our material and its loading condition, then Weber's constants is a pretty good way to go. Overall, we need to be able to use both the knot sensitivity factor charts and find our Q value from a chart, or find our characteristic length from Weber's constants from these polynomials. With that said, we've got the basics of fatigue, stress, concentration factors.